Welcome people to the pre-seminar. Today's speaker is Rudolf S from the Czech Technical University in Prague, and he's going to give us an elementary introduction to graded geometry. Please.
Thank you. Thanks, Thomas, for having me here today. I have to say there are way more people here than I thought. All right. So the purpose of this pre-seminar, as I hope I understood it correctly, is just to bring us all to the same level so that we can understand Valentina's seminar later. So, okay, to this end, I hope this won't be too basic for those of you who do know something about graded geometry. All right, so let's call this somehow informal introduction into graded geometry. Is this readable? Yeah, I guess. Okay, awesome. So, very well. Sort of the structure of what I'm going to talk about is first introduce like two main graded ways of grading manifolds, namely the Z2 grading called supermanifolds and the Z grading. And there are other ways to do graded geometry. I might mention those, but not go into detail. Then we will introduce an extra sort of element, an extra sort of structure to these graded manifolds, namely a special vector field. See what happens, what kind of structures we get this way. And finally, at the end, I hope I will be quick enough to introduce, basically just say the definition of L-infinity algebras. Those of you who work with those know way more about those than I do, so I'll just say the definition, basically. All right, so sort of the starting point here I would like to use is some common ground, right? Namely smooth manifolds. Before we grade something, it's, I think, advantageous to think of smooth manifolds in the following way. So you have some sort of a topological space, right? Call it M. And on this topological space, you have a way of assigning, I might use some colors here. You have a way of assigning to every like an open subset, right? An open subset of M, and you assign to it an algebra of smooth functions in this open subset. Okay, so this assignment, let's call it just C infinity, is in fact a sheaf. Those of you who work with sheaves know this immediately. Basically, this is just it, right? You take an open subset, you assign to it an algebra of smooth functions. And this has some properties, right, that I won't go into, but the most, I guess, useful one is that locally, one has coordinates, right, that exist coordinates. Let's call them xi. Right, and then every function locally, you can just write as a smooth function of the coordinates. I just do this. This is not very surprising. Nor should it be. But I think it's a good starting point for graded geometry, just to reiterate these things, because in a for graded geometry, the main idea is to have this side sort of the same, but make this guy bigger, more interesting somehow. So you go from just the sheaf of smooth functions on the topological space to a sheaf of something, right? And this something differs based on what kind of grading you want to do. So first, if we want to do supermanifolds, I'll call them Z2 manifolds also. Then you want this object to be a Z2 graded algebra, super algebra. Right, so for every U, this is a super algebra. What that means? Well, in particular, it's a vector space over the real numbers, and it can be decomposed into two parts. So an even, shall we say, and direct sum with the odd parts. It's really a graded vector space with the Z2 grading. This can be also thought of as degree 0 and degree 1. And the same way as a vector space is this simple, in the same way as this is an algebra, so is this a super algebra. So first of all, elements, you can have an element of this that does not belong to any of these. But if you have a homogeneous element, so if you have an f from the even part, you say that f has parity even, or degree 0, but with supermanifolds, I'm going to stick with the word parity. And I'm going to denote it somewhat unusually as parity of f is 0, or even. And if you have a g here, the parity of g is odd. And you can multiply things in here. This is an algebra. And if you multiply f1 and f2, if these are homogeneous elements of this, then the parity of this is, of course, the parity of f1 plus the parity of f2, modulo 2. And furthermore, you want this to be commutative, but graded commutative. So it commutes, but with an extra sign to f1. Otherwise, it's just an associative unital algebra as any other. Okay, so that's basically it. Can I move here, or should I erase it? Okay. Okay. So just as we had coordinates, here, so is this not any possible like algebra, super algebra, but we also have coordinates here. Locally, there also exist coordinates, but now like two sets of coordinates, usually noted as x and xi, with different indices generally. And as you might expect, the parity of the x's is even, and of the xi's is odd. Right, and locally, every function here, or super function, I guess, if you want. I'm not going to use that word. So if you have coordinates on U, then f can be written as basically a polynomial. So let's go with A1 sub A. Okay. It's a polynomial where the coefficients are just smooth functions on this U. And these things are, I don't know, something. Right? Graded coordinates, you can think of them as formal variables, whatever you like. Okay, so locally this looks super, super simple. Okay, so that's it for supermanifolds. Now for these were supermanifolds. Any questions so far? Right. So now, the other grading I wanted to introduce are I'm going to call them Z manifolds. Right now, the grading here referred to the functions being even or odd. There's a Z2 grading. Now, if we want to have a Z grading here, we would like something like this. We would like the sheaf to be, again, a direct sum, but of overall integers of some. Like this. Okay, I'm going to put this into quotation marks because depending on how much you want to be like mathematically correct, this works for you or it doesn't. So strictly speaking, this construction, if you want to do this construction, it doesn't give you a sheaf. So that's something you really, really want. You want this to be a sheaf so that you can, I guess, compare functions locally, right? Glue functions together from local representatives. This gives you a pre-sheaf, but not a sheaf. But I guess this is the way most people think of the graded functions. So if you want to think of it this way, I guess that's correct. Okay.
May I ask a quick question? So here the problem with the sheaf, is it because you also have negative degrees, or
No.
would this also fail if you just take positively or non-negatively indexed ones?
Yes, thank you for the question. Sometimes when you go just from 0 to infinity, some problems disappear. Not now. Now this fails to be a sheaf even for non-negative grading. Basically, the reason is simple. It's just because we have a direct sum here. So the elements of this are finite linear combinations. Right? If you want this to be a sheaf, then you want for every open cover and every collection of local functions that agree on overlaps, you want them to glue to something. But you can have an infinite open cover here, just an open subset made up of open subsets that don't intersect with each other. And you can have, I guess, a function of a different degree, every one, and they don't glue them. Yeah, technical reason. All right. There are ways to fix this. I don't want to go into too much detail, but before we address that, what I want to say is that functions here can have a degree. I'm going to call it a degree now. I call this a parity here, denoted by b of f. I'm going to call this a degree of f, denoted by an absolute value. And this is an integer. And again, as before, what happens is that the degree of the product is just the sum of degrees. And the functions commute with an extra sign based on the degrees. Right. So this is it. So just a side remark how one can make this work. There are actually there's more than one approach. The usual, I guess, liked approach is one that works for just non-negatively graded manifolds. So if, let's say, OM U J is 0, like this, you can define a Z manifold. In this case, you would call it an N manifold, or sometimes an N manifold. The nomenclature is not super set. So an N manifold can be defined as a supermanifold. So it's a supermanifold, but with an extra grading. Okay, so as a supermanifold, I'm just going to write vaguely with compatible extra grading. Like compatible here just means that if the degree is odd, then the parity is odd. All right. What? Yeah. Yeah. Is that? I'm a big fan of the super muffled whatever. Okay, so the other way is like sort of technical, not take a direct sum here, but define this. You can define this as basically a sequence of these component vector spaces. So I and Z. So basically you just say that inhomogeneous elements don't exist. Yeah, this is sort of non-intuitive, but the advantage is that it works. It gives you a sheaf, everything works nicely. Anyway, this is just a like mathematical side note. We can all think of the Z-graded functions like this for our intents and purposes. Okay, so let me check what I want to say next. And, yeah, okay. Maybe I'll write here that due to the possible presence of negative degrees here. Okay, first thing, there are also coordinates here. Once more, we have coordinates. Once more, they are written, not surprisingly, as this, where the xi's have degree 0 and again have the role of the regular coordinates. And the xi's now have degree here, which can be positive and negative. So unless you work with non-negatively graded manifolds, which is often the case, but if you don't work with non-negatively graded manifolds, you have both positive and negative degrees, and you have to allow that. Yeah, my use of space is not very good. I'm just gonna have to move to the next one. Sorry. Okay, so we have to allow f, a general function in the coordinate neighborhood, shall we say, now is not a polynomial anymore, but you have to allow infinite polynomials, right? You have to allow a formal power series of f. I can write it this way as before. Psi 1 like a because these can okay, if there's a coordinate there which is odd, it has an odd degree, and it's to the power of 2 or higher, then it's 0 for obvious reasons. But we have also even degrees and also even degrees of negative even degrees possibly. So there can be an expression, you can have psi1 of degree 2 and psi2 of degree -2. The product has degree 0, and there can be infinite powers of this guy. And it's a valid function of degree 0. Okay. That's for the functions on Z-graded manifolds. All right. That should be it for the general introduction of these graded manifolds. So just think of those as manifolds, but with an extra large sheaf of stuff, of functions. Manifolds with extra peppers or something. Okay, so let's move on to Q manifolds if there are no questions. There are no questions, then Q manifold is just it gets a little bit confusing because you can have super manifolds that are Q manifolds, or you can have Z manifolds that are Q manifolds. Either way, you just add Q, unsurprisingly. What is that? It's a degree 1 vector field. So vector field, degree of Q is 1, and it squares to 0. And since the degree is 1, squares to 0 is the same as saying that it commutes with itself. Right, so what is a vector field on a graded manifold? So regardless of whether you have a super manifold or a z-graded manifold, you have this guy, which is an algebra, or graded algebra, and you can just say that a vector field on U is a derivation of this. Simplest, by far, definition. Right, so it's a linear map that takes, it's a linear map of this degree. Right, so first of all, okay, it's a linear map such that this is true. That means this is exactly the meaning of saying that it's a map of degree, this. And there is the graded Leibniz rule. So you can have this plus, and there's the ubiquitous sign here. You want to exchange Q and F, so you always put here the degree of Q and the degree of F, and F, Q, G. Right, and for supermanifolds, just write the parity here. For supermanifolds, you can only have even or odd vector fields, but the definition is the same. Right? So why would we want to introduce this kind of a vector field of degree 1 and that squares to 0? So let me answer that question with an example. The best kind of an answer, I think. So an example, it's also a first example of a graded manifold that we see here. So take a vector bundle. This is a regular smooth, just a smooth manifold, nothing graded here so far. You can do, however, you can do something to it to make it a graded manifold. To make it a super manifold, you can do parity shift if you want. This is a capital Pi. So this is for super manifolds. And for graded manifolds, you can shift the degree by any number. In particular, you can shift it by 1. Z, graded manifold. Okay, what does this mean? So on a vector bundle, when you have a local trivialization, you have this kind of coordinates, right? You have coordinates on the base, and then you have some sort of a frame for the local sections. And you can take the dual of this, and these give you coordinates on the vector bundle. So these will be the coordinates coming from the dual of some frame, local frame here. And we will just denote these as xi. And you see where I'm going with this. Right, so to make this a super manifold, you basically just declare these xi's to be odd. And to make this a degree shifted manifold, or degree shifted vector bundle, a Z manifold, you declare the degree of these things to be 1. And you could have any k here, and then there would be any k here. This is a very specific example of making graded manifold. It's a simple graded manifold. They can be much more complicated. Anyhow, the point here is these two guys are sort of similar, almost the same. Right? The details, the differences are mostly technical. I'm going to work with this guy because I'm more used to it, but the same discussion applies here. The discussion of what are the functions here. The functions here, let's go with global functions for simplicity. So of degree 0, locally, I said that locally functions on a Z manifold look like where was it? Right there. From power series of the appropriate degree. But if here we only have coordinates of degree 0 and of degree 1. So the only way to make a function of degree 0 is to have no graded coordinates there. So these are just the smooth functions on the base. Right? What are the degree 1 functions? Okay, let's write it explicitly. So f is a degree 1 function. That means f is a linear combination or a C infinity M linear combination locally of these things. Okay, and if you have a g of degree 2, I'm going to simplify the notation, sorry about that. Then g is, again, C infinity M linear combination that looks like this. Then you see how it progresses. So very simple shape of these functions. But if you look at where these guys came from, they came from a dual of some frame. The frame of the dual, in other words. So by making this a graded manifold, you don't change how these things transform when you transform coordinates. So these still transform as a frame of a dual of this guy, sections of this guy. So from this, we can just look and see that, let's stick with the local, global sections. So any functions of degree j are the same thing as sections of the jth exterior power of the dual. Right, yes, thank you. Thanks. Okay, and from this, you can maybe see why I like this grading better than the super grading, because here we explicitly see that the functions of degree j are the jth exterior power. Right? The super grading would only preserve the parity. But I mean, the result is the same, mostly. It is the same. So the functions on this graded manifold are sections of the exterior power of the dual. Okay. So what happens when we introduce the vector field? Okay, so a vector field is a derivation of the algebra of functions, but this is the algebra of function. So any vector field is a derivation of this module, if you want. So a degree 1 vector field that squares to 0 is a differential here. In particular, a nice example is when E is the tangent bundle. So the shifted E, this is the shifted tangent bundle. The sheaf functions is then the same thing as the exterior power of the dual, which are differential forms on M. So an example of a Q is just the de Rham differential. So the de Rham differential can be viewed as a vector field on this graded manifold. There's a result of So there's a result that Q such that Q at the Q manifold structure on every shifted vector bundle is the same thing as Lie algebraic structure on E. In this case, it would be the canonical Lie algebraic structure just with the commutator. This is a nice, very specific example of a Q manifold. And I think I'm running out of time. Thank you.
Okay, thanks for the nice talk. Are there some questions?
Thank you. I'm not sure if I understood the definition of a supermanifold. So do you still start with the topological space, like for a regular manifold, or is it just the sheaf?
Yes, you start with a topological space, usually Hausdorff and second countable, same as for smooth manifolds. Then you, I guess, define the supermanifolds as locally ringed spaces, right, with the topological space and the sheaf that is locally isomorphic to a model space, which is basically just saying that there exist coordinates.
Okay, thanks. And so every smooth manifold is also a supermanifold or
Yes,
separated manifold
exactly.
by choosing a vector bundle, but not every supermanifold is also a smooth manifold, I guess.
Yes. Yeah, every smooth manifold is a trivially graded manifold in this way or that way.
But is every supermanifold also a smooth manifold? Like, does every supermanifold arise that way?
Yeah, in the sense that the topological space, the underlying topological space here, always obtains canonically the structure of a smooth manifold from this greater sheaf.
Okay, thanks.
This word model space. So how would the model spaces of supermanifolds or Z-manifolds look like?
Yes, model space for a supermanifold is a thing that's usually denoted like this, or the line here, right, where these are just some non-negative integers. And what this is, here the topological space is just Rp, and the sheaf is the sheaf, like you take smooth functions, you can write this Rp explicitly, you insert the open set, and then you tensor this guy with the exterior power of the dual, I guess, of R. Right, so basically this just means you choose a basis here, you take the dual basis as the graded coordinates, and then every function here is a polynomial in this sense that I wrote over there. So every supermanifold is locally a piece of this guy, where you just restrict this to some.
And so for Z-manifolds, the idea would be similar, I guess.
Yes, the idea is similar. You just have to sort of work with the power series here. Well, just polynomials, but it can be infinite. So the construction of the model space is a bit more involved, but the idea is.
More questions? Maybe I can ask a quick one. So here for the example, so if you take a Lie algebra, let's say, and you view it as a trivial bundle, so just over a point, then I guess what you get here would be just a Chevalier-Eilenberg differential, right, for the Q?
Yeah, for the trivial representation, yes. Exactly.
Which then would also be a special case of what's written here, this theorem that every Lie algebroid structure corresponds to such a Q manifold. Okay.
Exactly. So if you take the vector bundle here to be just a vector space and you shift it, then you get a vector bundle over a point, and then every choice of this Q structure is exactly a choice of the algebra structure on the vector space.
Okay, cool. And then maybe just so now what is happening here is kind of, so you take functions on these super or graded manifolds and they somehow look like differential forms.
Mhm.
So could you now also take like differential forms over these functions of the graded manifolds? And how should I think about this? Because this is now differential forms of differential forms, right?
Yeah, exactly. I have no idea. Right? If you take vector fields over this, then you get differentials or derivations of ordinary differential forms. So we would have a dual of these guys, and I have no idea what they represent in normal geometry.
Okay, nice. Are there some questions from the online audience? If so, please unmute yourself and feel free to ask the question. Okay, seems not to be the case. Then let's thank Rudolf again. Sorry, I didn't see very quickly.
So you mentioned this in a definition of the Z-manifold that this does not define a sheaf, and then you mentioned two ways to fix it.
Mhm.
But if you have a pre-sheaf on some topological space, then there's always to get a sheaf,
Yep.
sheafification. What would happen if you take the sheafification here?
I think I didn't make any calculations here, but I think you would get a direct product here to make the sheafification. But this is not very nice to work with because it's like too infinite, I guess. When you take the duals of this, it sort of explode. Right? If you take duals of a dual of the direct sum, then it's just the direct sum of the duals. The same thing here. If you take a dual of this, it's just the sequence of duals. But if you take a dual of this, it's not the direct product of duals anymore. So yes, you would get a sheaf, but I don't know if you would get like the sheaf that you want to work with.
Okay.
You would get a different sheaf than these guys.
So the reason is more or less for convenience, it's just easier to work.
Yeah, for convenience, but also because it works, right? It gives you this local description that you really want. You want to work with coordinates locally.
Great. So let's thank Rudolf for the nice talk. Thank you. Now there's a short break and then we have the main seminar.